Let's get right into it, shall we? Welcome to this explainer. Today, we're exploring something, well, something absolutely massive that literally sustains our entire world. But here's the crazy part. It's completely invisible to us in our everyday lives. It's this vital natural resource that we literally walk all over, we build our cities on top of it, and we rely on it for our very survival. So today, we're taking a little journey into the hidden world right beneath our feet to unveil the science, the history, and the reality of groundwater.
Okay, let's dive into this. I wanted to imagine, just for a second, that every single time you step outside, whether you're walking across a paved city street, a grassy park, maybe a dry dirt road, you are more than likely walking on top of a vast, hidden ocean of fresh water. I know, right? It sounds like total science fiction, but it's an absolute geological fact. But how exactly does this water even exist down there?
First things first, we've got to clear up a really common misconception. Because when most people hear groundwater, they immediately picture these massive, cavernous underground lakes or like rushing subterranean rivers. But actually, scratch that. That's rarely the case. Groundwater is simply the water found underground that's filling up all the tiny cracks, the pores, and the microscopic spaces inside soil, sand, and rock. And when these water-bearing geological formations are large enough, we call them aquifers. So instead of thinking of the ground beneath you as an empty bucket just waiting to be filled, think of it more like a giant, super dense sponge that's holding on to an unimaginable amount of moisture.
Now, what's really interesting about this slide is how clearly it outlines the water's actual journey. You can see water flows downward from the surface, being pulled purely by gravity. It starts off traveling through what we call the unsaturated zone, which just means the gaps in the soil contain both air and water. But as gravity keeps doing its thing, pulling that water deeper, it eventually hits the saturated zone. Down there, literally every single available space between the soil particles and the fractured rock is completely filled with water. And that exact boundary line between those two zones, that's what we famously call the water table. To really grasp why this matters, we have to look at the staggering scale of this unseen resource. Groundwater makes up a massive 33%. So roughly 1/3 of the entire world's freshwater reserves. Think about that. It is by far our largest accessible reservoir of freshwater on the whole planet. And because it gets naturally filtered through layers of earth, it's actually relatively free from things like pathogens, turbidity, and contamination, at least when you compare it to surface water. It really is a pristine, dependable lifeline for the earth. All right, moving into Section 1, Ancient Connections, Wells and Water Philosophers. Because you see, our reliance on this hidden realm isn't some modern invention. We've been trying to tap into it since the very dawn of human settlement. I mean, just look at this incredibly intricate stonework. The use of groundwater traces all the way back to early human civilizations. A perfect example of this is the Mohenjo-Daro civilization, dating way back to roughly 3000 BC. Thousands of years ago, they were already constructing these elaborate, brick-lined wells specifically designed to store and supply drinking water. Obviously, they didn't have modern geology textbooks, but they intuitively understood that reliable, life-giving water could be pulled right out of the dry earth if you just dug deep enough. But here's the funny thing. While the ancient engineers totally knew how to get the water, the ancient scientists really struggled for centuries to explain where it was actually coming from. It's kind of a wild history to trace. Early Greek philosophers like Homer and Plato hypothesized that springs were actually seawater being pulled through subterranean channels under mountains and somehow magically getting purified along the way. Then Aristotle comes along and suggests, hey, maybe air just condenses in cold caves. It wasn't until a Roman architect and engineer named Vitruvius entered the picture that the mystery was finally solved. Vitruvius hit the nail on the head with the modern accepted theory. Mountains catch a ton of rain, that rain percolates down through the rock strata, and it eventually emerges at the base to form streams and springs. Boom, mystery solved. Okay, so that brings us to Section 2. Where does it come from? Because if we're constantly pumping all this water out of the ground, where exactly does it originate? Hydrogeologists generally classify the origins of groundwater into 3 distinct sources. First up, we have meteoric water. Now, despite the very cosmic-sounding name, meteoric water literally just means precipitation, rain and melting snow that infiltrates the earth from the surface. Then we have qanat water. This is water that got trapped in the pores of sedimentary rocks while they were actively forming millions of years ago. And finally, there's magmatic water, which is exactly what it sounds like. Water driven out of magma deep within the Earth's crust. But as this brilliantly illustrates right here, while qanat and magmatic water definitely exist, they are very minor sources. The overwhelming source of our groundwater is just meteoric water. Every single time it rains on a rooftop or every time snow melts in a mountain valley, that water is starting this really slow gravitational journey downward. It's infiltrating through the soil and actively recharging our subterranean aquifers. So, simply put, our underground water is constantly being fed by the everyday weather right above our heads.
Which leads us into Section 3, the invisible ebb and flow. So we know groundwater isn't just trapped down there forever, right? But how exactly does it rise and fall naturally?
Well, the water table is actually incredibly dynamic. It's constantly being pulled back out of the earth through two main processes, evaporation and transpiration. As the water table gets closer to the surface, evaporation kicks in and increases, quite literally pulling moisture back up through the soil based on the soil's capillary tension. Think of it like dipping the corner of a paper towel into a spill and watching the water climb up. At the exact same time, we have transpiration. Wherever the root zones of vegetation reach down into that saturated stratum, those roots act like giant natural straws, pulling the water up to sustain the plants. This means the actual level of the groundwater is intimately tied to the type of vegetation on the surface, the season, and even just the daily weather. It's a very delicate, living, breathing system.
Moving right along to Section 4, our most vital, unseen resource. And as we'll see, this delicate system we just talked about is really being pushed to its absolute limits by modern extraction.
Today, groundwater is the primary water source in arid regions, and it's a massive, crucial supplement in humid ones. I mean, we rely on it for large-scale agricultural irrigation, running heavy industries, cooling systems, and of course, supplying our cities and rural homes. But our capability to extract it, it's really outpacing the natural meteoric recharge in a lot of places. Just look at the data here. As far back as 1975 in the US, at least 10 states were heavily dependent on high groundwater use. And in India, by 2004, the data showed that the groundwater development stage, which just means the amount of water extracted versus what was naturally available, was over 100% in states like Punjab, Haryana, and Rajasthan. So strictly based on the numbers, they were literally pumping out more water than nature was putting back in. Now, looking at this global map, the distribution of these resources is super clear. So the crucial point is this: groundwater is everywhere. From the dense blues you see marking complex hydrogeological basins to the lighter shades in the more arid regions, it really serves as a dependable, relatively clean resource across pretty much all climatic zones. It is kind of the great equalizer of freshwater availability on Earth, mostly because it's accessible right near the point of use with relatively low development costs.
Which leaves us with a pretty critical reflection to wrap things up. We've explored what groundwater actually is, how ancient minds figured it out, where it comes from, and how it naturally ebbs and flows. But we've also seen the massive, frankly unprecedented scale at which we're currently extracting it today. Because it's hidden beneath the soil, its depletion and its pollution are mostly invisible to the naked eye. So as our largest and most accessible freshwater reservoir faces these invisible threats, it raises a really big question we all need to consider. How will we adapt our management, our engineering, and our environmental protections to safeguard this ancient ocean beneath our feet? It's definitely something to chew on the next time you step outside. Thanks so much for joining me for this explainer, and I can't wait to dive into our next topic with you very soon.